So let me please briefly enhance this introduction. So I'm indeed attached to the mechanical engineering department of TU Leuven. And it's perhaps good to know that in that department, we have a very strong and long tradition in process development. So additive manufacturing for us started about 33 years ago. And some of the very first experiments on metal processing at a time that additive was still referred to as rapid prototyping, some of these very early experiments happened in Leuven in our laboratory, and they still lead to continuous research since then. So that's what we do. We develop processes, and of course we are also interested in the applicability of those processes. But when we see claims like additive manufacturing is intrinsically sustainable, then we mainly think of the process itself. We do not think of what is it doing when those components are flying around the globe, because the virtue of that is perhaps more with the designer than with the process developer. So sustainability is a delicate word. When people claim that something is sustainable, it's really hard to prove that you are not taking more than your fair share of what the globe has to offer. The only way you could really claim that a process is sustainable is if it has a negative impact. And to my knowledge, well, I don't know any processes that achieve that kind of level of performance. So let's dive in and let's have a look. How can we now objectively quantify the impact of processes in general and additive manufacturing in specific? And what can we learn from that with respect to the potential for improving the category of processes that we are all interested in? Now, looking at what is typically covered in a process, we typically need materials. Materials need to be won somewhere, need to be excavated very often. So mining, drilling, all kinds of processes underlying our material supply. And then typically we are not happy with the raw materials, so we want it to be converted to either some special liquid, some polymers, or perhaps some granulates, some powderous material. Then comes the actual AM processing, very often followed with some post-processing requirements. And only at that moment does the real use phase come into the picture. Use phase is very much the virtue of the designer, of the application. End of life, you could say, well, we have launched parts, so we probably also have to take into account the end of life destination of those parts. When we have a look at who is to be addressed when we want to have information on these consecutive steps, or who could actually influence those steps, the bad news is we are spread over different responsible parties. We have material suppliers, and very often there are already a series of them. There's already a little chain in there. Then there's the actual additive manufacturing party, most of the time a single company. And then, of course, there is the end user responsibility. Okay, let's have a quick look. What does that mean for the processes that we are interested in, and especially how easy or how difficult is it now to get proper information with respect to the impacts that may be caused in these consecutive steps. First step, the material supplier. The bad news is that this is a very intransparent sector. You can get a price offer, yes, you can get material properties from these players, but if you want to know what is, for example, the energy intensivity of their production, if you want to know what is their efficiency, the news is that it is basically very difficult actually to convince them to open the doors. What we do know, and this is very much in contrast with a lot of studies that are being published, it's definitely not as simple that a kilogram of material and a kilogram of, for example, powderous material would be more or less the same thing. The yield of turning material into fine-grained particles with very specific dimensional requirements, and also when we are talking for example, about the sphericity of these powders, well, AM players are extremely demanding there. And the bad news is that in the production of these powders, a lot is being lost. Very often we are talking about yields of just 10, 20, 30%. And even worse news is that sometimes the non-usable fraction cannot even be properly recovered. Why? Because of high oxidation, for example. It's not as simple as just squeeze it back into the chain. So this is quite annoying, and as you will see further on, this does influence our footprint quite significantly. The good news is that for additive manufacturing itself, the actual processes, well, there are plenty of devices around. We work closely together with end users of such machines, measuring them, gathering data, measuring emissions from them. It can all be done, it can all be accommodated, and we have fairly good data there. Then comes again the end user, and I think we have seen some really nice examples of how additive manufacturing facilitates improved, well-optimized designs. Yes, we can save weight in aerospace components. Yes, we can optimize the fluid dynamics by having, for example, cooling systems completely tailored to the actual cooling demands. So as a result of that, we can make components, we can make systems that are fairly efficient in their use phase, but that's not what the process is doing. That's basically what the design is influencing. So zooming out to the processes most commonly used under the label AM, we have fused deposition, we have SLM, SLS as the main categories. And while the process chains are a bit similar, except for the material preparation, of course, in the case of fused deposition, we need filaments, typically from polymers. There is some tendency to try this also with metals, since fairly recent developments in this sector. We see the powder manufacturing from metals for SLM, and we see for SLS similar thing with polymers. So all the rest seems fairly similar. Now, for the rest of my presentation, we'll just squeeze out this use phase. We'll focus on the part where we have an influence as manufacturing players. The chain itself is a little bit more sophisticated than just a linear chain. Why? Well, indeed, there are possibilities for reuse of powderous materials, especially in SLM. Very fortunate that this is the case, otherwise the impact would be much bigger. And then we have the polymer case, in which situation we actually do have a fairly significant waste stream, and that one I'll document a bit further. Okay, how do we now quantify this impact that we want to objectively make object of our discussion? We use LCA techniques, has been mentioned before. Perhaps a very short introduction. What do we do to achieve that? There's a lot of things happening behind the scene before you first get your output data reported, as in the further slides. We look at the full material flow, the input material and the product coming out. We also look to unwanted effects like emissions and waste. We do have to acknowledge that sometimes we use process materials, for example, protective shielding gases, and of course there's the energy input. And then there are streams that are a bit more difficult to quantify. What do you do with byproducts, non-wanted products, but that may still be useful? What about the recycling of some of these streams? All of that is taken into account, and we make sure that we have a correct mass balance. Everything that goes in ever has to come out. So that's part of the rules of the game. Then when we have all those streams, we try to link them to impact categories. And I am aware that some of you are really very much fascinated by CO2 equivalents, by global warming. Why? Because it's a strong societal trend. But we have seen several times in history that there are shifts, there are fashions in this impact attention. Some years ago, acidification, for example, was important. So we shouldn't overlook the other effects than global warming. So how do we systematically measure these effects? Well, we look to all the streams and we translate them into equivalent streams. We know that CO2 contributes to global warming, but we also know that methane does the same and not to the same extent. So there are conversion factors, and then we can make simple additions, how much global warming potential, how much contribution to acidification. That's what we call classification and characterization in an LCA. I save you the little details, but there are lots of different impact categories. And typically, if you want the scientific content of an LCA, you have to look to this midpoint effects. We know that there is ozone depletion. We know that there is warming of the atmosphere, and there are so many other impact categories. But when you look at it from a societal perspective, basically we are not so much interested in the mechanisms, but more in the final effects. And the final effects are three different types of impacts. We are interested in human health, expressed in disability adjusted life years. We are interested in ecosystems, the disappearing of species. And we are interested in the long-term availability of resources. So resource depletion is another important category. And of course, those are categories of totally different nature. If you want to bring them together to a single score, which in the end we always like to have because we like to compare different things, well, you will end up having to choose a weighting scheme. Which one is more important, human health, ecosystems, or material depletion? It's a very difficult to answer type of question, and depending on who you ask, there are different categories of people in society. So you can only make a kind of an average based on statistics of sociologists. Okay, that's how an LCA works, and that helps to explain how do we get to graphs like this. This is a graph expressed in eco points, endpoint impact effect measured with a CIMAPRO recipe quantification method. I save you the details, but that explains how we can get to a single score for the different aspects of our manufacturing. And you can see here that, well, for fused deposition modeling, so the toothpaste technology, we can see that there it's quite simple. It's the electricity that is demanded by our systems. Our fused deposition machines are fairly slow. You know how long it takes to build a part. You easily spend a few hours, and processing over 24 hours for large parts is not uncommon. So the fact that this is so slow and that there is so much overhead systems in the machine explains how we get to such big impact of the electricity consumption. Simple conclusion, so easy to find out what can we do about that. How about the other processes? When we look into SLS, there the picture is totally different. The SLS printing itself here, the consumption of the machine is, I wouldn't say negligible, but is an order of magnitude smaller than the input powder. We took the example here, most commonly used powder, polyamide 12. Here you can see that the powder, as it arrives at the premises of AM manufacturer, is already having a big footprint, and the inefficiency that we use this powder is very much responsible for this huge impact there. If you split up a bit further, you can see that in more detail, the SLM process at the top, so the actual making of the part, and then the material production and the atomization, both together, they contribute similar order of magnitude that is by itself already bigger than the process demands. So the atomization, as I told you, is an inefficient process with demanding a lot of recycling. In this case, with polymers, it can be done, but this is already the case here of SLM. So this is material production, is the metal production, sorry. So when we are talking about titanium or stainless powders, well, the yield there is really not so very good. And this explains why the atomization is actually so demanding. Brought together an overview. So all of this was just to explain how do we get to graphs like this. Well, these are the graphs showing the actual production step. So the actual machine tool as we can master it and as we like to design it and redesign it. Here you can see for SLS and for SLM two different cases with different points of attention. For SLS, the waste material production is really dominant in the picture. Besides the energy, that's by far the biggest contribution. Also, compressed air is visible in here. Basically, that's also, again, an energy, indirect energy impact. So you can see that the waste material production, the fact that so much material cannot be retrieved in the process. Why is that? Because we still haven't achieved a level that we can retrieve the powders and reuse them at will. We know that the properties of the powders after processing are not really up to par with virgin material. So we can only at best mix them to a limited extent into the next batch. And we have to be careful there not to lose quality of the final output parts, which would be even more detrimental if we produce scrap. Nobody is happy with that. When we look to SLM, that picture is quite different. The waste material production there, if you have ever talked to people in this branch and you ask them how much waste are they producing, well, it's really very limited. On a yearly basis, we are talking about very limited volumes. A barrel of powder being discarded is already quite a lot. So the impact here is mainly in the production of the material, and then of course in the energy of the process itself. The material production is not really penalized here. Why? Because you can reuse that material many times, and when it leaves, the part itself is not taken as an impact. It's a functional device, so it's not really penalized to the process. We can see, however, that the assist gases, for example, the shielding that you need to do here at the time when this study was made, and I like to refer to the reference there, Callens, 2015, one of my former PhD students. Well, at that time, the shielding gas efficiency was still fairly low. In the meantime, machine tool builders have looked into that, and just avoiding huge losses of shielding gases is now a very common feature of most devices. So the good news is we can measure the impact. The annoying news for us was while we measured it and showed it to the world has been changing. Many of the machine tool builders we work with, they thank us for the data and then they change the machine, which is of course the very purpose, but that also means you have to be careful what sources you consult, because they grow old while you are reading them. Lessons learned, when we look to fused deposition modeling, basically it's the machine energy efficiency. Can we make faster machines? Can we avoid energy losses, heat losses, for example, in the extrusion nozzle? It's a technical target to reduce the energy demand. When we look to the powder-based processes, it's very much the feedstock we have to focus on. That means we have to work on the suppliers. Waste polymer powder is a problem for SLS, and the question is, well, I'll hand over the estafette stick to Tom Craeghs afterwards, because we are working together with Materialise on some strategies to indeed improve the efficiency there. How can we make polymers that are less sensitive for this clocking together, for changing the structure as an influence of the high temperatures that we like to process them in AM process chamber. The SLM process, that's even more difficult. There, the powderization is the big bottleneck, and finding better processes for gas atomization is, of course, a totally different task than improving the machine tools for AM themselves. Okay, so just to give you a glimpse of the different strategies that we are currently working on. Polymers, I'll show you some quick early results of strategies to switch to biopolymers. How about the powderization process itself? Can we perhaps think of less demanding materials, filler materials? Would that structurally change our parts drastically? The energy efficiency, the conversion that we are actually making, we are not consuming energy, we are just transforming it in our processes. But could we lower the footprint by the source of energy? Of course, that's an obvious one. The powder reuse rate is an important strategy that's fully under control of the AM manufacturer himself. And then, of course, well, what we call waste, is it really waste, or can we think of industrial symbiosis? Can our waste be a direct input for other processes that are less demanding, that do not need this high sphericity, for example, of the powder? A quick glimpse of first results as a handover to Tom. We have been testing together with Materialise different variants of polyamide. So switching to polyamide 11 based on some biopolymer. Well, we can see that indeed for some of the sensitive impact categories, like to the left, climate change, global warming, so the CO2 equivalents, also the fossil depletion to the extreme right. For those impact categories, we do have an improvement. The bad news is that for all the other impact categories, we actually see that this biopolymer is less performant, is having a bigger footprint. And you can understand that if you know how much effort has to be done to grow this the materials underlying the biopolymer, the land use, the water use, the toxicity of the fertilizer, and all the protective measures that farmers have to take against rodents and insects. All of that contributes to impact. So if you focus on only CO2, this looks like an improvement, even a significant one. If you look to impact in total, it's basically not. It's the bad news. Biopolymers by themselves do not really help. And that is shown here. You can also see here the refresh rate, the rate to which you actually need to add new virgin material to your container is a very important factor. And the influence you can have by choosing the polymer, well, actually the influence of the refresh rate is much and much bigger. But you can also see that with a single score impact, polyamide 11 here sticks out, is not better than the polyamide 12, unfortunately. With that, I'd like to hand over or to refer to Tom, who will explain the strategies that Materialise is developing for further lowering their footprint as a major producer. And well, up to the chair, whether we keep questions for after this dual presentation, or you like to give an opportunity to the audience at this moment.